Okay, good morning again, everybody. It is 9:30. Welcome to it. Happy Tuesday, everybody. So welcome to the first day of the 2025 ISSR Research and Development Conference virtual technical sessions. We're very glad to have you all here, and we're really excited to have a really neat set of presentations for you about all the great work being done in low Earth orbit on the International Space Station. My name is Jim Way. I'm Executive Director of the American Astronautical Society. Our organization has been responsible for assembling these technical sessions for the ISSRDC for the past several years. AAS is a nonprofit technical society. We were founded in 1954, and we bring together people to discuss the challenges and opportunities associated with exploration in science and space. So once again, we're really happy to have you all here. And, we've just enjoyed our collaboration with the full team at the ISS National Labs and at NASA, making it possible to bring all of this really important research to all of you. While we're not sure right now what the future holds for these technical sessions, we do know that a lot of the event content from the ISSRDC will be included in AIAA Ascend conference that will take place in Washington, D.C. in May of 2026. So keep an eye out for that and attend if you can. So now, without further ado, I'd like to introduce the chair for this first session. Please welcome Narasimha Prasad, who is from the NASA Langley Research Center here in Virginia. So Prasad, take it over.
Yeah, good morning, everybody. And I'm sorry the video is not coming through. My name is Narasimha Prasad. I am an aerospace technologist here at NASA Langley Research Center in Hampton, Virginia. And I am your chair for this session. Here is how we will proceed for these virtual technical sessions. We will present the first 5-minute executive summary. We will then open up for questions for that author. We will then move on to the next presentation and author, and so on and so forth. After each presentation, we will have that author come on screen and begin the question and answer from anyone here in the webinar. Webinar attendees will not be able to come on screen, so please use the question and answer tool to submit any questions you might have. If you have time left at the end of the session, we can address any additional questions that might come along. By the way, if you want to see the full 20-minute presentations, please visit the online program and open up that file. Now, let's start with the first presentation. Thank you.
Okay, first presentation's about to get going here.
Good morning. My name is Nazrin. I'm a fourth-year PhD candidate in the Department of Chemical and Biomolecular Engineering at Lehigh University, and this morning I'll be talking about my work on dual measurements of thermal gradient-driven and Brownian motion in glycerol water solutions in ground and microgravity conditions. So our work focuses on developing a particle separation technique that can be used in diagnostic devices to separate viral particles for their easier identification. We use colloidal polystyrene particles and apply a temperature gradient to drive motion through thermophoresis or directional motion parallel to a temperature gradient. To quantify how complex fluids, such as biological fluids, affect thermophoretic motion, we measure viscosity or the resistance of fluid to flow orthogonally to particle velocity and analyze our data using classical particle tracking for microreology. When we apply a temperature gradient in ground conditions, buoyancy-induced recirculation or continuous mixing can align with or oppose thermophoretic motion, which complicates our measurements. And this is our main motivation in running our experiments in microgravity conditions. So our samples consist of fluids with fluorescent probe particles that we pipette into glass capillaries and adhere them to a microscope glass slide. We measure temperature with thermocouples on hot and cold sides and use copper shims underneath the sample to create a sharp temperature gradient. We image particles through fluorescent microscopy, and on the right is an image of our setup in the microgravity science glove box on the ISS, where we remotely operated the objective and the camera to take images like these. So the bright spots are the particles in our samples. To analyze our data, we use the classical particle tracking algorithm for microreology, which I'm happy to explain in detail if anyone has any questions. We track the particles to get their x and y positions, and from particle motion in x, we measure velocity parallel to the temperature gradient and fluid viscosity in the y direction. And these dual measurements allow us to correlate how the sample properties affect particle velocity. And in this particular portion of my work, we measured viscosity of glycerol water solutions in ground and microgravity conditions and compared them to tabulated viscosity data. And these results tell us how well we can characterize local fluid properties at the same time as measuring particle velocity. So our main results are that in both ground and microgravity conditions, we got accurate viscosity measurements in these glycerol water solutions, which validated our methodology for use in complex systems. And interestingly, we didn't measure any velocity in microgravity conditions, but the velocity in our lab experiments on Earth closely followed the trend of recirculation velocity due to the continuous mixing of the fluid under gravity. And this tells us while there was no thermophoresis in microgravity, we can estimate how much velocity will occur in ground conditions. And we're excited to continue using this technique in more complex solutions such as polymer or thermoresponsive solutions. And this data is essential in characterizing how convective motion can affect complex biological samples and really aid in developing separation techniques for viral applications. So I'd like to thank our funding agency, Gilchrist and Schultz Labs, TechMasters, the ISS National Lab, and KBR Inc., and the Expedition 72 crew for handling our samples in space. Use the QR code if you'd like to see our journey in remotely taking our microgravity data and follow our work as we learn more about particle motion under temperature gradients. And thank you for coming to my talk.
Oh, thank you so much. And Jim, did you ask everybody getting the video? Because I'm not seeing the video on my screen. So I wanted to check everybody's seeing the presentations.
Sure. Please, somebody can maybe open in the Q&A thing if you saw the video or not. Just, one or two people. Yep, we saw video,
Awesome.
so it's
Okay,
working.
no problem.
Good.
So,
Yep.
the first question is from Paula Jenik, and she's asking any Z-scale measurements 3D that you have conducted?
Hi, good morning. Can you hear me okay?
Yes.
Okay, yeah. So thank you for your question. So all of the particle tracking that we do is in 2D. So we just measure motion of particles in X and Y direction. And in our work, for example, any motion in the Z direction would mean that the particles are going in and out of focus. And so we're not able to track them. We fortunately haven't seen that happen in our ground or microgravity experiments, but we mostly measure motion in X and Y directions. So I hope that answers your question.
Okay. Just a question from my side. Where did you do the microgravity experiments?
So the microgravity experiments we did on the ISS, and our setup so the microscope has been there since last year, and it was used for some experiments that were running prior to ours, and our experiments, we were running them remotely in, I think, November last year, and we got some extra time in March this year. So the microgravity data is from the ISS, from the Microgravity Science glove box, and then the ground experiments are from, our lab here at Lehigh University.
So you had a telemetry link, a duplex link?
I'm not sure I understand.
No, where you looking at the experiments, like daily basis or some periodic basis, or was there a link looking at the experiments?
So we operated the objective and the camera through LabVIEW, and we had a couple of weeks of a lot of time where we were able to come online and run the operate our system remotely. Yeah. So
Okay, thank you.
thank you.
Thank you so much. And if audience have got any questions, please let me know, or you can type it in the question and answer section of your video.
Now, Zine, was there anything else that you just wanted to mention just about your science? And any big aha moments for you? Anything that, you said, oh, wow, that was cool.
Yeah, we did actually see a lot of very interesting stuff in so we sent several types of samples there. So the first was the glycerol water samples to just kind of validate our technique, and that's what I was presenting about today. And then we saw a lot of very interesting things with thermoresponsive solutions. So that means like there's a polymer molecule in our sample. We heat it, the polymer molecule collapses. So we saw a lot of really interesting particle motion with that we actually didn't expect to happen. And then we went back to the drawing board, referred back to literature. It does actually happen, but now the interesting question is, does it happen the same way in both ground and microgravity conditions? And that's kind of our future work section that we're really excited about.
Fantastic. Maybe, Prasad, maybe time for one more?
Yeah, there is one more time. One more question, please. If there is.
Sure. Oh, yeah.
Okay,
So,
there is a question
yeah, go
there.
ahead.
Okay,
Yeah.
Professor Roshan Adhikari, does microgravity have a varying effect on Brownian motion of fluids?
So since we measure Brownian motion through the y direction in our systems, we measured the correct viscosities in our samples. So no, it actually does not affect Brownian motion of fluids. It occurs the same way in ground and microgravity conditions.
The next question is, what contract vehicle did you use?
Do you mean how the samples were delivered to the International Space Station? Because if that
I
is the
think
question, is that
I'm not sure. There is no name for that attendee, but I suppose you can go ahead and answer that way. So about the
yeah.
platform, yeah.
So we kind of hitched a ride with one of the, I believe, I don't remember exactly which flight it was, but it was shipped as like cargo on one of the flights to the International Space Station. So it was not with the crew, it was with I believe other
Oh, okay.
supplies that were delivered to the ISS. So I hope that answers the question that you were
Okay, thank
asking
you so
about.
much. Yeah, the next question, how did you find out about ISS research? What was your experience throughout the process?
So I found out about this research by starting my PhD program at Lehigh University. So while I wasn't there for the development of this proposal, um, I think it's been a very interesting experience because it's definitely unique because we're using gravity as kind of a variable in our studies. Um, Definitely unlike a lot of projects that
Okay,
I've encountered. So
thank you so much. And
yeah.
the last question is from Sarah. That did they mean who was your implementation partner?
So okay, I'm going to assume that by implementation partner, you mean the people who helped us
Yeah.
develop this. Yeah. Okay. So we worked a lot with TechMasters Inc. They're in Huntsville, Alabama, and they actually 3D printed the holder for us and helped us develop a very well-controlled heating and cooling system. And we worked a lot with the folks at ISS National Lab to make sure that all the experiments that we do are up to protocol and are safe to run on the International Space Station.
Thank you so much, Nazeen Asanova, and we will move on to the next video.
Thank you.
Good afternoon. Today I'll be talking about the effects of microgravity on mini-channel flow boiling. If you enjoy, please check out the full talk. Flow boiling in reduced gravity has been investigated by several groups using drop towers and parabolic flights. These experiments focus on how bubble shapes differ in microgravity and also investigate critical heat flux. These experiments are inherently short-term studies since they offer a few tens of seconds of microgravity time. To obtain more extensive and long-term data on how microgravity affects critical heat flux in particular, NASA built the flow boiling and condensation experiment to run on the International Space Station. We used the flow boiling and condensation experiment to look at transients and instabilities between flow regimes, but first we need to assess the steady state behavior of the system. We can highlight some of the differences between ground and ISS experiments using the boiling number. The Nusselt numbers are generally higher on the ground, but converge at low and high boiling numbers past CHF. The more effective removal of vapor bubbles seems to be the difference up until CHF is reached. We notice that CHF occurs at approximately the same location for both cases. However, there is about a 15% decrease in Nusselt number on the ISS as compared to the Earth. We also took a look at the pressure, and we noticed that there's approximately an 8 kilopascal difference between the two cases, which corresponds to the hydrostatic forces or hydrostatic pressures that arise due to the fact that the experiment on Earth is oriented in the upwards direction. We also notice that for higher boiling numbers, we start to see that pressure drop increase. This can be associated with the fact that we have more vapor in the channel, and when we have more vapor, the volume expands, and because the volume expands, the velocity has to increase, thus decreasing the pressure at the exit, which increases the overall pressure differential. In addition to performing experiments at constant flow rates, we also performed experiments where we varied the flow rate. Similar to the past experiment, we kept a constant pressure of 130 kilopascals and an inlet subcooling of 10 degrees Celsius. However, this time we kept the heater power constant at 40 watts and started out with a flow rate of 40 grams per second and decremented that in 2 grams per second increments until we reached the minimum specs of the flow boiling module at 4 grams per second. At each step, we waited for steady state to be reached to take our data. As we see here at high Reynolds numbers, there's very little difference between the 1G and microgravity. However, at low Reynolds numbers, we see a big drop off in the ISS. This corresponds to the fact that there's less hydrodynamic forces to move the bubbles along the channel, and we lose the buoyancy force in microgravity. We see some discontinuities here in the data, and this has to do with how we had to run the experiment. Due to the extended length of this experiment, we would generate heat soak throughout the whole system, and we'd have to shut the system off and let it cool down before we started again. So that's why we see this in 3 parts. We see that same in the temperature data. Although we set the set point at 54 degrees C, which was 10 degrees subcooling, we did reach towards the later runs before we shut off and reset. The temperature did increase a bit here. So that just explains the discontinuities there. In conclusion, steady state flow boiling data on the ground and the ISS show that the overall thermal performance on the system is affected by gravity. However, these gravitational effects diminish as the flow rate increases and as the vapor quality decreases. We also see these effects diminish as the heat load is decreased. At the higher flow rates tested, when CHF occurs, is not affected by gravity, and a 15% decrease in Nusselt number is observed aboard the International Space Station. Though the heat transfer coefficient deviates between 1G and microgravity, the boiling curve appears to be universal, at least for the flow rate tested. This universal boiling curve was best fit by a sigmoidal function, and future work will report on the transients that occur as we change the heater power levels and as we change flow boiling regimes. These results certainly may differ if different fluids, such as water, are involved, but MPAFH is perfectly wetting for both the copper and plexiglass that the channel is made of, and was chosen as a surrogate for cryogenic propellants that NASA is key in investigating.
Okay, Prasad, if you're coming on, please unmute. While we're waiting for Prasad. Hi, Alex. Glad to have you here.
Hi, thank you very much for having me.
All right. Let's see. First question from.
yeah.
Oh, go ahead. No. Go ahead,
Sorry,
Prasad.
it was muted. Thank you so much. And this is a question from Nazreen. And what was the time scale for your experiments?
So all the experiments that we presented today were steady state, and we let the system run for about 5 minutes before taking the data. And then we took the data over a course of 10 seconds and then averaged it. I hope that answers that question.
Okay. And there is a second question is from Sachin. The 15% decrease seems rather modest. Is that in line with what you expected?
So at the higher flow rates that was tested there, we did expect that to see not a huge impact from gravity because we have that inertial force that is pulling the bubbles away from the wall. At lower flow rates, we'd expect that 15% decrease to increase to have a larger deficit where there's less of that inertial force.
Thank you. I think those are the questions. And thank you so much, Alex. And if there are any
Actually,
more questions, please let me know.
I've got one real quick.
Sure.
What's the most, what do you see as the most practical application of your work going forward?
One of the most practical applications for this is cooling. I didn't really touch on this in the brief executive summary, but I do go into it a bit more in the full summary, especially when it comes to microelectronics. We produce a lot of heat in a small area, and getting that heat away is really important. And we want to see how these systems can be used in space because they're very commonly used in gravity. But we want to see how these systems fare when we remove the gravity component, since buoyancy is a large factor in these systems.
Great. Thank you.
Thank you so much.
I think we're on to the next one.
Yeah, let's go to the. Yeah, thank you so much. And let's go to the next one. Yes.
Hi everyone, this is Samuel Falano, and today I will give an executive summary of our work titled From Terrestrial to Microgravity, a study of solar structures and properties under extreme temperatures. Before I move on, I would like to point out that majority of this work was carried out by my colleague Dr. Manish Kumar, who graduated last summer, and this was his PhD research, and now my PhD research too. I would also like to acknowledge my supervisor, Professor Sid Patak, our funding agencies, and scientists from NASA. Moving on, in microgravity, understanding metal joining parameters and joint integrity in any joining technique under extreme temperatures in space is critical for the safety and success of future space exploration missions. And this is because principles that guide the process in terrestrial conditions, such as heat and mass transfer, are not the same in microgravity conditions. In these conditions, phenomena such as thermocapillary effect are more evident. In this project, we primarily focused on microgravity versus terrestrial solder joints because solder alloys are low melting alloys, due to which they experience the largest change in microstructural and mechanical properties under extreme temperatures. Also, they are an important class of materials for in-space manufacturing and metal joining, as they serve as mechanical and electrical connectors between components in electronic packaging and are used for mechanical and pressure joints. Moving on, three main science questions in this research have been developed. First is what factors contribute to the accumulation of voids, micro and macro segregation in microgravity sodas. And based on the samples we got that has been gotten from ISSI, we have been able to understand why these microgravity sodas have more voids compared to terrestrial-based sodas. And this drives our second question, which is what are the potential void mitigation strategies? And we are currently planning a new experiment in spring 2026 where a new soldering experiment will be done in microgravity with precise control over key parameters, unlike the previous experiments where these parameters were not controlled. We will also be investigating 7 different solder alloy systems with varying surface tension properties, as you can all see on the screen here. Likewise, we will also study the different solder alloy designs, which are the reflow spreading specimen, the reflow filling specimen, and the reflow spreading specimen for small coupon. This is for us to study 3D distribution of voids and different faces in various sodas. And the third question is, how do extreme temperature conditions affect the soda properties? In this, I'll discuss how extreme cryogenic temperature affects soda joint, focusing on beta to alpha phase transformation and ductile to brittle transition in tin-based soda alloys. These are two competing effects that are tied to their microstructure. Where if we have like a coarse microstructure, this helps reduce the formation of beta to alpha tin transformation, but reduces the temperature at which ductile to brittle transition will occur. From our micropillar compression experiment on terrestrial tin silver copper soda alloy at cryogenic temperatures, it was observed that there was an increase in yield strength and stress at instability at cryo temperature. Also, the plastic strain at instability is reduced under cryogenic temperature, and we observed like a saturation that was being occurred at minus 40 degrees Celsius, which means there's probably a ductile to brittle transition around that particular temperature. We also studied the different deformation types that were observed in each pillar good type, and also compared properties such as strength, stress, and plastic strain at instability, where group 3 micropillars, which is the eutectic region, exhibited the highest properties. This is our ongoing work, and here we are studying this different soda alloy system under these extreme temperatures. Thank you.
Thank you so much. And it's open for questions. Please type in the question and answer section, or you can come on the chat if you have any questions.
So I think I'll jump in. Samuel, nice work. So it looks like did you say you just went up on the recent resupply mission, right? Or on NG-23?
Yes, yes. So our flight is going to be going up to International Space Station next spring.
Oh, next spring. Okay, got it.
Yes, next spring. So that's when our flight is going to be going for a new set of experiments whereby we are going to be able to control some soldering parameters as compared to the previous one that was done about 20 years ago. So with this, we're able to understand how we can mitigate the voids, because voids has always been a problem whereby when you solidify solders in microgravity. So we're trying to understand how the voids can be mitigated through studying different solar alloy systems across different composition.
Fantastic.
Yep.
Thank you. Who is your implementation partner?
Can you come again?
Okay.
He asked, who is your implementation
who is your
partner?
implementation partner?
Oh, okay. We are working with Voyage Technologists, formerly known as the Tech Masters guys and everything. So those are our implementation partners. Yes, we are working with them hand in hand. So they are the one producing the black box, like where this set of sodas will sit in that will be sent to the international station. So what we are doing in our lab is we are preparing those samples, whereby we send them there, then they couple everything, they make sure everything is fixed, then they send it to the International Space Station.
Thank you. The question from Marufa. What are your findings in the presence or absence of microgravity? And also a compliment. It's a great presentation.
Okay. Thank you. So, like I said in the presentation, that most of this work was actually done by my colleague, Dr. Manish Kumar. So, but one thing, when I was able to figure out is, so for the microgravity samples, they was observed that there were much voids. They were larger, bigger voids compared to the terrestrial sodas. And the conclusion he was able to come up with is due to the absence of what we call due to the absence of buoyancy, whereby the air can actually escape the sodas. But in microgravity, that's not the case. So we observed that there were like much voids in microgravity as compared to the terrestrial sodas.
Any more questions? Thank you so much. This was a great presentation, and Jim will let us move on to the next one.
Thank you.
Hello everyone, I hope your days are going well. I'm Joe Adam, and today I'll be giving you an overview of the ring shear drum, an apparatus operating on the International Space Station for fluids research and microgravity. This ring shear drop, or RSD, is a 1-inch diameter drop of liquid pinned between two titanium contact rings. Containment is achieved solely by the surface tension of the liquid. Flow is driven by the rotation of one of the two rings, producing shear within the drop. Mixing then occurs subsequently based on secondary flow from inertia within the fluid. An example of this is just demonstrated through a campaign in 2021 using human insulin that was studying fibrillization in the absence of solid boundaries. This is related to things such as amyloid diseases where fibrillization is in contact with fluid interfaces. Upon deployment, the initial shearing then can commence, followed by prolonged shearing, which in this instance demonstrated gelation within the drop due to fibrillization of insulin and amyloidogenic protein. Upon extraction, structures on the interface become apparent, showing how important this interface can be to changing the structure and function of proteins. At a fluid interface, there is a unique opportunity for proteins to unfold and change their shape. This occurs in diseases such as Alzheimer's, Parkinson's, and infectious prions, which ultimately becomes a fluid dynamics problem within the brain. Fluid interfaces act a bit as a physical catalyst, something that will change the conformation of a protein, allowing its structure to more easily perform certain interactions. This follows a protein stability network, meaning that minimizing this energy will be spontaneous, and interfaces producing potentially unwanted effects can impact things like fibrillization, going from a monomeric subunit to much more complicated networks of materials that may be undesirable for processing, drug development, or native structures such as disease states like these neurological diseases. Because of this complex rheological focus, the ring shear drop has been tailored to rheological measurement. Here, startup flows are shown in human and bovine serum albumins, showing that you can impulsively start the ring and then measure the particular aspects of the fluid during that startup time, steady shearing, and subsequent stop. This was performed with 2 different serum albumins during a 2022 campaign with these serum albumins, also investigating computational flows within the system. Of course, this needs to be balanced with systems on the ground, here being the knife edge viscometer, a particular ground-based system which uses a dish for containment as opposed to surface tension, allowing ground measurements to be corroborated with those in space. This curvature of the interface is also important. During extraction, we actually undergo many different shapes, from spherical to subfilled sphere, cylinders, and catenoids. The profile of this interface can be captured with AI image analysis, determining a profile that can be compared to numerical simulations of the interface. Extraction is under hydrostatic conditions, a non-shearing state. However, a flow model could be conceived of where these shapes are subsequently sheared to produce multi-geometry rheometry within the drop, in a sense allowing a single apparatus to behave as multiple different viscometers, different flow devices because of the surface tension containment. Preliminary results as a proof of concept with very viscous human serum albumin of 400 milligrams per milliliter were conducted this last June 2025 as an initial measurement towards adopting the RSD as a multiple fluid measurement device under different flow regimes, different shapes, with different test fluid configurations. With that, I'd like to wrap up this overview for today by acknowledging all the people I've worked with, including the laboratories here at RPI, NASA, NASA Marshall, Jim McClellan, our chief engineer, as well as all the astronauts who have worked on this project. Thank you for listening. I hope you enjoyed, and have a nice rest of your day.
Thank you so much, Joe. And it's open for questions. Please type in your question in the question and answer section or chat. Let me start with my question. Can you elaborate on your surface profile measurements?
Sure thing. We actually use a big old Facebook's algorithm, Meta, to first get a profile, a mask of what's on the interface, followed by standard canny edge, which gets a profile, and then that can be physics informed, saying what are the possible shapes. And really the only necessary part for the AI element is for speed. Being able to do this at every single frame this happens. If you want to measure jizzer or shake or any kind of perturbations as such, you can do so in a dynamic sense. Classical methods would function as well, just slightly slower.
Thank you. There is a question from Sachin. He compliments about the videos. They were very nice. And the question is, what do you quantify beyond video? Torque or particle tracking on surface?
So particle tracking, but it's all through the video. That's all what's being used as our raw data. We do have a microscope as well, but that usually is used in the static configurations, hydrostatic, because any motion is going to be much, much faster in that microscope. You need a lot higher frame rate. So it is all through particle tracking velocimetry, and then there is a lot of depth determination based on what's on the interface or what's inside the bulk of those drops.
Thank you so much. And any more questions?
Yeah, just what do you see as the kind of the most beneficial next step in your research path?
Sure. So one of the largest ideas is really furthering that multi-geometry rheometry. If I had to throw a couple buzzwords out, going through some of the calculations and the computations on how would maybe something that's not so standard of a fluid, non-Newtonian fluids behave in space, things like blood, things like cerebral spinal fluid, that we know change quite dramatically in astronauts, and even other life forms like E. coli or microorganisms can benefit a lot from gas transport and the flow of these fluids. And if you're interested in the modeling, you might just see it in a couple minutes here.
Thank you so much. And one more question. What was the temperature range?
So all this is ISS room temperature inside the MSG, and that's about your 21 degrees C plus or minus half a degree or so. It's a little bit better. We actually do not measure temperature inside of our test cell, but it is taken to be the ISS room temperature.
Thank you. There is a compliment from Shahab, just mentioning that the talk was very nice. So,
Well,
any
thanks.
more questions, please? If not, let us move on to the next presentation.
Thank you, everybody, today. Nice having you here.
Thank you so much.
Hello, my name is Patrick Underhill, and I'll be providing the executive summary of our work doing interfacial modeling of protein drops that have been sheared in microgravity. This work is motivated by the microgravity ring shear drop aboard the International Space Station. My colleague, Dr. Joe Adam, will describe in detail the ring shear drop, in which a protein solution can be contained between rings by surface tension, and then a flow created by rotating the ring. This work considers numerical modeling of the flows. The bulk fluid is considered nearly Newtonian, but the Reynolds number is large enough that nonlinear inertia is important. The interface is treated as a non-Newtonian material, in which the parameters in the constitutive equation can evolve relatively slowly. And we include nonlinear two-way coupling between the bulk fluid and the interfacial motion. In the full presentation, we compare the flows in this ring shear drop to an Earth analog, the knife edge viscometer. For example, here we show the interfacial velocity, v, as a function of radius at the interface for different values of tau, which is a dimensionless yield stress in the interface. The black curve, the tau of 0.01, represents essentially a Newtonian interface. As tau increases, the interface gets thicker and thicker, and stiffer. Inside the rings at small radius, it acts like a straight line, like rigid body rotation. Outside, near the outside dish at an R of 2, the fluid essentially stops because the stress is below the yield stress, and only near the ring will the interfacial material deform and move. We also show results performing COMSOL finite element calculations in the microgravity ring shear drop geometry using the mesh shown here to resolve the fluid flows. Showing one example result here in which we computed the azimuthal velocity at the interface as a function of angle or location along the interface. The fluid in blue with the smallest yield stress tau acts like a Newtonian fluid and rotates like nearly a rigid body, whereas the larger yield stresses actually deform more than the lower yield stress material. This is the opposite of what you might expect and what is found on the Earth analog knife edge viscometer. Thank you for listening. We'd like to acknowledge support from NASA, the ISS National Lab, our implementation partners, as well as support from Tyler Mucci, Cesar Gonzalez, and Nate Carwick with the ring shear drop, and also thank and acknowledge all of the many astronauts that have helped with the ring shear drop.
Thank you, Patrick. Thank you so much. And now it's question and answer session. It's open to questions. If you have any questions, please type in the section question and answer session section. Let me start with the first question. You talked about interfacial velocity. Has it been validated?
So we're working on the validation in some of the ground analog situations, and that's where we've done have the cleanest interfacial tracking, which I show in the full presentation, where we can track particles and compare with our simulations. In the ISS experiments, we're working on the particle tracking to try to compare with our simulations.
Thank you so much. And there is a compliment. The presentation was really impressive. So just waiting for more questions.
I'll ask one. So yeah, you said something, you found something, was the opposite when you got up to when you actually got into low Earth orbit. Was that your biggest surprise from all this research?
Yeah, I think the fact that the difference in microgravity and the different geometries that you can have really changes this kind of nonlinear combination of many phenomena at the same time, of the fluid mechanics and the non-Newtonian materials and inertia, and all of that working together can make the trends be the opposite of what we expected.
Fascinating.
Yeah. Thank you so much. And any more questions? Jim, if you have no more questions, we could go to the next presentation.
Yeah, thank you.
Hello, everyone. Thanks for joining. My name is Ryan Jensen. I'm president here at IRPI, and today I'll be talking about microgravity fluid phenomena on ISS. We'll start off by briefly talking about the impact of geometry on low-G fluid mechanics and capillary phenomena. These are drop tower tests, and we go from 1G to 0G. On the left, we have a circular cylinder, and on the right, we have a triangular container with a corner, and you can see that it generates a very different response where there is pumping and the liquid migrates to the top and the bulk gas drops. And so the key idea here is that geometry significantly impacts fluid behavior in a low G environment due to surface tension. So some of the first experiments that our team did aboard ISS, and I should say the first experiments, were the capillary flow experiments that were performed in 2004 and beyond. There was the original CFE, and then there was a CFE2 suite of experiments. And these probed various behavior like contact line dynamics. And in this video here with the vein gap experiment at the top, the importance of, or the impact of, corner angle and distance from the wall. You can see the ellipse in the vein. As that vein is moved, it sweeps out different angles and different distances from the wall, and you see different fluid behavior where there's wicking or not wicking. And then the bottom one with the ICF, the interior corner flow channel, we investigate the impact of a taper in the geometry to passively migrate the bulk ullage downward and then have pumping of the liquid upward. Now, obviously, there's no gravitational vector here. This is all low G aboard the International Space Station, but you can see how geometry impacts bulk orientation, wetting, and even phase separation in the bottom right video. We talked a bit about geometry, and now we can talk a little bit about wetting, specifically non-wetting or superhydrophobic surfaces. And in this video, you see on the left a drop tower experiment where the liquid jet goes along the race of the surface because it's superhydrophobic and then breaks up into droplets. We were actually able to deploy a superhydrophobic kind of ping pong paddle as part of the contingency urinal experiments, as you see in the top right there, where a jet is impacting. I think that's a red drink and bouncing off. And then we improved that surface in a 2.0 version that is monolithic, very robust, 150 degree plus contact angle, regenerable. And you see that on the bottom right there as well. Now, when you combine geometry and this non-wetting, you get an interesting behavior where in this drop tower experiment, the liquid is in the vertex and then is passively expelled and propelled through the channel because of the non-wetting behavior or the superhydrophobic behavior and the geometry of the conduit. All of these concepts were combined in the ISS tech demo of the collapsible contingency urinal, which was selected for the Orion missions as a backup contingency urinal. It includes superhydrophobic elements, superhydrophilic elements, geometry, and all sorts of fun stuff. So if you are interested in that, check it out. There's several items published around this, but it's a good example of all these combined technologies. We also investigated some geometric aspects and dynamics related to pipetting and well plates, developing some different geometries to investigate and how to mitigate this droplet, satellite droplet issue that you see there. Further, we deployed some of this wedge geometry for a few things here, which is a liquid amine CO2 scrubber. This could also be done with an ionic liquid, but a whole bunch of small wedges were deployed. And then also this CCHX, which was a capillary condensing heat exchanger. Further, for the plant water management experiment on ISS, we were able to deploy several fluids management technologies, including a water trap diverter, a bubble diverter, I should say, bubble separator, and even the planter channel, which all perform different phase separation operations. Finally, the combination of all this work, from the fundamental low G testing to fundamental science aboard the ISS, and then technology demonstrations, has resulted in a variety of devices, subsystems, and hardware that we're developing. Just a sampling here on this slide of kind of different components that have become kind of custom COTS that can be deployed in an accessible, cost-effective manner and really impact exploration going forward. If you'd like more detail, check out the in-depth presentation or feel free to reach out to me at rjensen@irpillc.com. Thank you.
Thank you so much, Ryan. And this was a great presentation. And it's open for questions now. Let me start with a question here. You talked about super hydrophobic characteristics, and how did you measure those contact angles?
We measured them optically here on the ground. In space, we also tried to measure things optically, so not extraordinarily precise, but we were able to get good results with good magnification and good image processing.
No, okay. The second question is, what is your immediate application for these fluid management techniques? Any applications to biomedical or drug delivery type of pharmaceutical applications?
Yes, we've been kind of focusing on lately. We have some wet lab stuff, so kind of redefining some of the hardware for things like well plates, syringes, just kind of operations. And then we also have some work going on related to sample preparation. And one of those is, trying to streamline the containment and the lysine process and things like that. We're working with a partner in that handles the, kind of the bio part, but working with them kind of on the engineering side to make sure we have the containment right, that we have the fluid management right, that we can do all those things, and then do them in a, the key thing we're trying to drive to is easier methods or more streamlined methods to do all the science aboard station, new stations, et cetera, without having, more cumbersome facility requirements. So that's something we're striving for, but in process.
Okay, thank you so much. And there is a question from Professor Roshan. The interfacial velocity should bring about difference in value of surface tension in space environment. Is such a possibility pronounced?
I'm not sure I understand the question completely.
Should I
I'm not
repeat
sure,
it?
yeah. Maybe repeat it. I'm not sure I understand it, but go ahead and repeat it, and I'll try it.
Okay, interfacial velocity should bring about difference in value of surface tension in space environment. Is such a possibility pronounced? That's the question.
I'm not sure. Most of the work that I'm familiar with has been related to kind of these bulk reorientations, fluid flow, and the surface tension is a factor, but not the primary factor for us. It's primarily geometry and wetting characteristics, but the wetting characteristics too are flexible from kind of more of an engineering perspective. So, plus or minus X% is okay for the kind of engineering design that we're doing.
Thank you.
I don't know if that answered the question.
Okay. Amir asks, how do your measurements compare to surface evolver simulations?
Very good. So our team developed the CFIT stuff. So another version of Surface Evolver, it's a little bit more user friendly. We do a lot of Surface Evolver work around here, and they fit very well. So we do that to kind of preempt what's going on in space, help design our experiments as well before they go up. But generally, we're engineering with that tool in play. I'd say very well. I would say one thing about the original vein gap experiments was there was a bulk reorientation that you probably saw when the thing was measuring. It didn't show up in the surface evolver. That was because you needed deeper convergence, and there were some further runs afterwards that we did where you could actually see that reorientation, but you had to converge for quite some time. Just a note there.
Okay. The next question is from Sarah. For us science-friendly folks, would this type of research help implementation partners better put liquid-dependent research projects together? Other practical use applications? Anything in regard to bathroom design, drinking fluid, etc.?
Absolutely, 100%. Yeah, that's what we're trying to do. And so, yeah, we have actually a new urinal system that's going up. That already went up last week. So we're doing some fluid stuff with that for the toilet systems. For the assisting the science, that's a key thing. We have some concepts for microscope slides, keeping flat surfaces, for investigations. So we are trying to kind of interface. And if anyone wants to reach out in the, doing bio experiments, we are trying to give those folks the tools and respond to the tools that they need so that they can be successful. Because obviously there's lots of fluids interactions going on, lots of different types of fluids, non-Newtonian, Newtonian, et cetera. And so I think the engineering and the science have to kind of meet together and work together so that the experiments that are built are thinking about all the things that need to be and implementing the hardware and technology like we're talking about so that they can be successful, but also, like I said, robust, reliable, repeatable, and cost effective. I think that's an important thing to do is to.
Thank you. Thank you so much. A question from TB. How does oblique or non-Newtonian act in this microgravity environment?
Yeah, so non-Newtonian we haven't done a ton. The principles are still there. You just have different certain fluid properties. We've done a little bit of investigations with some kind of we did some like slime stuff, which behaved kind of funky. But I would say that that's something that would probably be a good area to explore, especially as you start adding different types of biofluids and even blood and things like that can be a little bit different. Typically, those perform similarly, but once you start changing properties, and those can act a little bit different. We've seen.
Thank you so much. And one last question from Lionel Parker. I think there is a compliment. The videos were very helpful to understand the experiment, and that you pointed out the various COTS products that were used.
Yeah, yes. Thank you. Thank you. Yeah, we're trying to like I said, make things accessible, develop these things in response to the community and the science community. So thank you.
Okay, one final question. It came from Joe Adam, and foaming has been a historical problem in microgravity-based systems. How do yours compare?
I think you said foaming.
Yeah, foaming.
Yeah, yeah. We haven't done a ton with foams, to be honest with you, in low G. That might be an area of research and development, or if there are applications specifically, would love to hear about them or work together on them. But haven't done a lot with our team on foams in board ISS yet.
Thank you so much. And I think
I've
go
got
ahead,
one more
Jim.
just real quick.
Yeah.
Just, might be a really stupid, obvious question, but drop tower versus microgravity, big difference, just duration and everything.
Yes. Yeah, big difference. What we had done is use that as kind of like a feeder, with a drop tower, low cost, very accessible, at least the ones that we had used. And so you can kind of just do a whole bunch. I mean, we've done over 10,000, but those have fed into ISS experiments and have helped form those and help make those very successful. Because if you know what, even though it's 2 seconds, you scale it, you can get very good information. And then you're not, just surprised when you get to space. So I would say they're complementary, but the ISS stuff is absolutely necessary, the long duration stuff, and especially for a lot of the application stuff, you just really have to do that. Yeah.
Yeah, makes sense. Good. Thanks.
Thank you so much. And I think, Jim, let's move on to the last, I suppose, next presentation.
Thanks all.
We're just checking, not sure if there's any audio with this one. It was a very late submission. Okay. I guess that's what we get with that one. And unfortunately, we don't see that presenter present with us today. That would be Chatham. Please, Chatham, if you are on, or if somebody from that presentation is on, raise your hand in the chat, but I don't think we see anybody on from that. So, Prasad, not sure if we have all our panelists back, but if anybody else has any other questions, follow-ups for any of the panelists, any go-backs, things like that, please go ahead and post them in the Q&A tool. And just while we're waiting on that, just a reminder that these sessions are being recorded, and so they will be made available online via the ISSRD site and the AS site as soon as possible after these sessions conclude this week. And we just want to appreciate, send a quick comment of appreciation for everybody attending today. So let's see. Renee
Jim,
Bell is saying there
Renee
was
Bell,
voice in the TLC presentation. So should we try running again?
Maybe that, yeah.
Emily, go ahead and try running that one again. Click on that little speaker thing in the middle, maybe.
could be noise. Let's see.
Yeah, we're trying. We're not getting it.
Yeah.
All right. Well, the full presentation should be available online if you all want to see it. We do have a few comeback questions coming in. Let's see. From presentations from the non-presenters due to cancellations be available with the rest. No, mostly if they were, I mean, if they're posted on, if the presentations are posted online and the person isn't here, they'll be available, but most of the withdrawals were without presentation, so we don't have any for that. John Allen, your question on Lisa on ISS, I'm not sure if that was directed toward anyone. Renee Bell is raising your hand, or Kevin Sims. Not sure. Let's see.
There is a question from Erika.
Oh, okay.
Will we expect later sessions to hold to the published times in the program, or we?
Good question, Erica. Yeah, if there is a withdrawal or somebody doesn't show up, we'll just move forward. We're not holding to specific times, a 10:30 or 10:04, something like that. We'll be doing that. We'll just go right through and keep going that way. So thank you, Erica.
Any more questions on any topic or any presentation so far you have heard?
Okay. I think we're good to conclude with this one. So Prasad, take it away.
Okay, thank you so much, and thank you for coming and attending this session. And also, I thank the presenters for their valuable contribution to the ISS R&D. And this concludes this session, the first session. And again, thanks to our presenters, and thank you to all the attendees who joined today and asked questions. Reminder that all presentations are available online, and these webinars are being recorded, and they will be made available as soon as possible after we are done here. And again, once again, thank you so much for attending this session.